actually have to have a person to evaluate it, and then they would have found that nope, there's nothing here that is offensive or inappropriate. So it has got to be an automated engine of some kind that detected content that is inappropriate. So when they reviewed it with using a person, they go like, "Oops," but they didn't bother to send me an email to say that, "Yeah, sorry, we made a mistake. Everything is reinstated." They didn't say anything at all. So I can tell you more stories about my dealing with YouTube and what kind of trouble I had to go through, but we kind of need the time to talk about class stuff too. So we'll go ahead and start with all the class stuff. Is the browser looking okay? Because I'm using a smaller area on my screen to project onto the projector. So is that looking okay? All right, good. And it we'll double check OBS, make sure the volume is good. So that seems pretty healthy. So we are good to go. Using the older computer, OBS, with OBS running in the browser, the CPU load would be about 30 something percent, and right now it's only about 6.5%. So the new computer is definitely a little bit more spiffy. All right, so we are going to take a look at the new homework assignment, which is called recursive calls, because I think we are ready for that. And we'll take a quick preview. So there are a few questions, where, it should be pretty easy to answer. Like this question. Something how value. So don't say out your answer, because I think most of you should know that answer by now. And then the second one is, how are parameters passed from the call? The answer is correct. Just as a catch-all, right? And then we have question number 3. So question number 3 really is the beginning of this entire quiz, because the first questions that you the recursive version, figuring out the and then with a particular value. Okay. So once again, keep your answer to yourself. Now the biggest question is this particular function. So that's basically what the fourth question is about. The fourth question is asking you to implement the function and then turn in the mnemonic code as your answer. So that is the implementation of the recursive using TTPA. All right. So for those of you who are not familiar with Fibonacci numbers, you can just look it up. Fibonacci sequence, and then the first link is probably the correct one. At Wikipedia. So this is basically what you can read a little bit about it. Donate money to Wikipedia, and then what. It's just later. So F record. Is that okay? So that means you have to understand a few things to get this program to work. So I'm going to show you some sample programs. Each individual one will address a particular issue that you have to deal with when you are working on this program, but none of it is going to give you the entire answer all within the same program. So the first one that I'm going to use is something like this. Okay. I'm pretty sure we have used this before. And this is 7. Whoops. Indentation. Double R. That's kind of one of the thing about this keyboard is it bounces a little bit, so I tend to double tap or double key certain characters. So I have to find a way to fix that. Okay, underscore T. We'll make this 12. So you might think, oh, we're just going to return the numerical value of 12. Nope. We are going to return the return value of 5 plus the return value of 7. All right. Is that okay? So now the implementation of these homework assignment to the Fibonacci homework assignment is up to you. You have to kind of think about the connection between the Fibonacci. Okay. So I'm going to start up a new notepad to represent the assembly code. Is this font okay? Or do you guys want it a little bit bigger? Just bigger? Okay. All right, so we go to Edit, Preference. Let's try 13. Okay. Is that better? 13 works? Okay. So I'm going to do the same thing with the other one. Oh, okay, it's automatically updated. Cool. Okay, so let's go ahead and implement the subroutine 5 first. We use the name 5 as the label, okay, and then we have to specify the return value of 5. Okay, and then we have the usual return sequence. So the usual return sequence has LD, B. I cannot use A, but I can use B or C in this case. So LDB works. Increment D, and then we have JMPB. 7, yeah, it's kind of the same thing. We just need to copy and paste a whole bunch of stuff, change one line, and we're done. Control C, paste, change that to 7, and we're done. Do we have any questions about this part? Copy these 3 lines of code just to return at the end of a subroutine. Is there a better way to do it? Okay. Well, but you're right. There is a better way to do it. In other words, what I say when I'm in the 5 plus 1. Which one are we going to change? Mm-hmm. 5 plus 1. On which line are we going to? Well, but I'm in charge. I can modify the code. I can add a new opcode. Remember, each op has up to 16 instructions that we have. Singles. So I got the assembly, which is byte, one single byte. And I'm not only saving in terms of the number of bytes in the program, I'm also saving the amount of time to fetch the opcode, because when I have one single opcode, I'm saving, which is kind of significant when you comes to of a program. Okay, so if I did that as an approach, I would have turned the TTP. Sorry. So diagram out the difference between RISC versus, or have you done that already in this class? A little bit? Okay. Maybe a little bit further this time. Do one that versus as few instructions as possible, but we'll have finding a sequence of instead. It's the trade-off. Mm-hmm. I left enough room, to make that happen. But it's kind of in general, where you can do more, and the hardware of the processor is going to get complicated. So what is the trade-off then? You have a more complicated processor, but each instruction can do more, as opposed to a simpler hardware, a simpler processor, but in order to get something done, you might need a few instructions to get it done. The main trade-off. I think some of you remember the argument. Data center dissipation. So it is related to power, because most power consumed by the bottom line is what kind of architecture amount of energy to perform the most amount of computation. That's the bottom line. We care about this processor can finish like 6 gazillion computations per second. If it takes up too much energy, not that becomes the bottleneck. Okay, so processor get the most work done with the least amount of architectures of more. Okay, it's a little digression. I want the sequences of using these sequences of instructions instead of a single return instruction. Routine can get back to the caller supposed to go back to, and how it is utilizing the stack. Because otherwise, if you make a return instruction, then what you'll be seeing visually is that. Does that show you what is happening on the stack? Not at all. Does it show you that you're modifying the stack pointer? that you're retrieving something from the stack and then you're deallocating that thing from the stack, doesn't show you anything at all. So that's the reason why I kind of continue to use that approach. Okay, class setting, it does help. Stack is being used from a subroutine to the caller. All right, so now we can move on and talk about 12. So when you look at 12, okay, and we are not going to cheat, okay, so we are not going to say, oh, since we know, this is 5, this is 7, 5 plus 7 is just 12. If we want to stay truthful to the C code, what do we need to do? Okay, we have to call 5, and then we have to call 7, add the values that return, and then it becomes own return. Okay, so let's go ahead and see how we do that. So we first have to call 5, okay? So once again, in most architectures, that's all you need to specify, call 5, okay? It doesn't show you anything about what is happening on the stack. It doesn't show you anything about, oh, we have to save the return address, or we have to allocate bytes on the stack at all. So we're going to do it the old-fashioned way in this class. We use 4 instructions to do that one single thing. Okay. So the first thing is we have to compute the address, the return address. So it's .6 plus. Okay. Remember, this is postfix notation. Register A, the opcode executes. Nope, it's the address of the LDI opcode plus it. So why is that address of interest to me? Let's find out what else we need to do here. We need a decrement D to allocate 1 byte on the stack for the return address. And I can comment it too. So we are allocating byte for the return address. You can see how it's double character, because the bouncing of the keyboard is not the same as my other keyboards, so I have to kind of get used to it. And then the next one is the ST instruction, because once you allocate a space on the stack, you better do something with it. So this is actually storing the return address on the stack. Once we have set up the return address on the stack, it is time to actually continue execution in the subroutine. So this is when we jump to 5, which is the entry point of the subroutine. So these 4 instructions, okay, typically on most modern architectures is combined with a single opcode, CLL. So that one single opcode, call 5, you wouldn't be able to happening underneath. We're going to stay with a cumbersome way of doing things in this class. All right, so now what do? Well, when we get back, okay, so I'm going to put a location here. This is, okay, once again, double, key here. This is the return the place to return to, okay. So the whatever instruction I put here is let's do some counting as an instruction. 2 bytes. after the write of LDI instruction. So by loading into register A does have the return. It's the same thing as the old way of doing things. Name of that label really is exactly the same, except this time I do not label at all. That part okay? All right. So at this point, register A now has the value of 5, okay? But I don't know, I cannot do anything with that value yet because I don't have the second number, which is 7, okay, or the return value of 7. If I call 7 right now, okay, so which is eventually what I need to do, okay? So let's say, we call 7 here. By the time 7 returns, the return value of 5 would have been lost. Is that making any sense? Because by the return value. So if in the second register A, what am I going to do? Okay, because I need to save value after 7 returns, then I need the value of the return value of 5 and add the return value of 7 to the saved value of the return value. So what should I do here? Yep, we'll use the stack. Very good. So instead of using some random location in RAM and do some allocations, I'm just going to use a byte on the stack. So the way to do that is simply to decrement D and then the stda. So by doing this, I am saving the return value of 5 on the stack. Okay, or if you prefer to use a more accurate word, we are pushing the return value of 5. Key is itself does not or JM byte is the opcode constant you want to utilize in the instruction. Instructions only take 1 byte. So are we okay at this point? Getting back to saving the value, the return value of 5 on the stack. Is that part okay? So right now, on line 28, we have both values somewhere. Okay. So let's look at this scenario here. Register A has the return value of 7. Okay. And by the way, I just answered one of the questions in the lab release today. Where's the other one? The stack pointer points to the return value of 5. Oh, okay, so we now have both of those numbers. But I cannot just stack. It is not in a register. I can only perform addition of 2 registers. I cannot perform an addition at a location in RAM. Now, this is an cisp processors. In many cisp processors, you can do that. Actually add the content of a location in RAM to a register directly. Okay? does not, because I'm doing it as simple as instructions are. So I have a in multiple instructions. So what do we need to do now? Well, it sounds like we need to retrieve that byte from the stack. So that means we have to do a load instruction, put it into something other than A or D, okay? B is fine, okay? And then we deallocate that byte on the stack. So these two instructions combined is basically popping the return value of the second call, which is the first call, excuse me, of 5 into register B. So at this point of time, register A has the return value of 7, register B has the return value of 5. We can now perform the addition. So we have add AB. It has to be in this, okay? One of the questions, okay? And after this, I'm all done, okay? So now it's time to specify the 3 lines of code to return, which is LDBD, increment D, and then JMPB, the usual sequence of returning from a sub. Are there any questions about routines in this particular? No questions? Does anyone want to test this code? Okay. That's good. I like that answer. I like it when you guys are skeptical and do not trust me. All right, so we'll go to the Google Drive. Okay. I have to make a little automated mechanism that can detect, where I'm looking. So when I'm looking at something that's close, it will automatically flip that thing down. If anyone in this class wants to get rich really fast, make eyeglasses that have autofocus mechanism. Okay. In other words, there's a little distance sensor, and also a sensor that detects, I'm looking. So when I look at it that way, you can see that okay, you're looking at that distance, and it will automatically adjust the strength of my glasses to correct my eyesight. If you can make that, you'll be rich. There are a few technologies that can help you that sort of thing. The first one is, how do you know which way I'm looking? That's the first question. Okay, it's actually very easy. That technology has been around for some time already. So the way you do it is you look at the you very weak infrared light on my eyeball, and then you look at the reflection of that light relative to my pupil. So when I look at in different directions, that relative position will change, and you can use that to deduce where I'm looking. Is you have 2 cameras on the frame of the glasses, and then you can use triangulation to figure out what is the actual distance to the object that I'm looking at. Okay, you can either do that or you can use LiDAR or many other different technologies to do that. So the biggest question, the biggest challenge is how do you change the strength of the prescription of my glasses? Okay, now huh? Exactly. So that technology has been around in cameras, right? You change the actual, length or the positioning of the lenses in order to change the strength of the lens. Okay, but that's really heavy. Okay, So I don't want to, have a helmet, on, just to get that feature, right? Okay, this is not a head-up display. I don't want to look up like a Apache, helicopter pilot. Yeah, just that I can get that feature. So the other technology is to have a lens that is flexible. So instead of having a glass or plastic lens, you have something that's made out of flexible material, and then you have motors at the back of the frame, and what it does is um, it pulls a string, okay, so it can basically stretch the lens to flatten it to reduce the curvature of the lens, or it can relax and let the lens to get back to its original shape. And guess what? That's how your eye naturally focuses. It's only when people get old, like me, then the lens gets a little bit stiff. So despite my eye, trying to pull it and flatten the curvature, it could not do that anymore because the lens itself has hardened. Is that okay? Of course, you can even think of even a cheaper solution is to replace my lens, in my eye. Just get rid of the old lens, replace it with a new synthetic lens, using material that has the same flexibility as a natural, biological lens. So that would be awesome too. Yep. Oh, I suppose it doesn't help because if we do LASIK, right, it doesn't help because LASIK, my after correction vision is better than 20/20. So there's nothing wrong with my eyeball. It has to do with the lens in the eye and not change its shape. I can focus on things at you. So LASIK can help me focus on a particular distance perfectly. So I can get rid of my, nearsightedness. Okay, so I can take off my glasses, and then LASIK can say, what distance do you want to focus at? Infinity, about this distance, or the cell phone distance. But once I choose that distance, it will only be sharp at that distance. So it doesn't really get rid of the problem or solve the problem of I need additional lenses to look at things at different distances. Yeah, so for those of you who are younger, way younger than I am, there's a lot to look forward to as you age. There we go. All right, so here's the program, and you can see how all the symbol stuff get resolved really fast now. And I think I might have some leftover code from before, so let's get rid of that because it's giving me some additional error messages because of that. So we get rid of that, and everything should be good now. There we go. So we'll go ahead, but this program is not done yet because the first thing it's going to do is 5, which is not what we want. Okay, so I have to redo the copy and paste because I can't just insert a row in the spreadsheet. That's going to mess up the assembler. So we'll go ahead and let's see, what is the quickest way to do this? We'll just do main here. LDID with 0, initialize the stack pointer. Instead of using a local variable to store the result, we're just going to do the call, and then we'll do a halt right after that. So we'll just have to look at the value of register A when everything is done. So to do that, we have the usual call sequence, which is LDIA with .6 plus, decrement D, store A to where D points to, JMPI to 12, and then when it comes back, it's time for a halt instruction. In other words, my main single value of 12 to a local value. So I just need to check register A to see right value or not. Is that okay? This is basically as simple as it gets. When to see whether it works or not. Okay. So we'll do a copy and paste here. And by the way, this really helps. Yesterday I was having so much trouble just looking at my own screen. And today is like, yeah, I can see it. There we go. So now we go to File, Download as CSV. And we'll call this 12. All right, time to start up the start LogicSim. Do you guys like the Y format better than the kind of VGA? Yeah, you see more, right? So load image. It's called 12.csv. There we go. And I'm fairly sure it works, so I'm just going to do a Control K without setting up the log. So here's Control K. The program has stopped. I need to check a few things to make sure that everything is good. The first thing I'm going to check is the program counter. It is at location 09, which means the halt instruction should be at location 08. Okay. So we switch back to the assembler, go to the Assemble tab, and make sure that the halt instruction is in fact at location 08 in hexadecimal. That works. Okay, that's good to know. The second thing I would check is to look into the register bank. There are two things to check in the register bank. The first thing to check is the return value. A has 0C, that's good, okay? Because 0C in hexadecimal is 12 in decimal. And then the second thing I want to check is to make sure the stack pointer is balanced. It is back to 0, 0, so that's good because everything looks good. This particular sample program, which contributes a little bit to what you need to do. Is that good so far? All right. So let's go ahead and move on to the second thing that we need to do with your homework. So I'm going to use a different sample program to illustrate that. So let's go back here and go back here. So I'm going to take this out, and this time we'll implement a fairly useless subroutine. Okay, so this useless subroutine is like f. It takes one single parameter, which is an unsigned 8-bit integer called x here. Okay, is that the wind or the rain outside? Both. Okay. Sorry? Yeah, but I was sleeping. I was sleeping really well last night. Maybe it's because the house was swaying. When I lived in Hong Kong, I was on the 11th floor, and that was in the middle of that particular building. The top floor was 20th, and there are now many people who live on like 50th floor, 60th floor in a residential building. When you have a building that high, in a typhoon. You're on like a 40th floor, the magnitude of the swaying is not only detectable, it's going to be significant. If you have a teacup on the table, you can probably see the level of the teacup going like this in a storm. Huh? Hong Kong is not in an earthquake zone, so kind of good. But it does have typhoon in the summer every year, big time. So we'll say that if x is less than 2, stronger than usual? Wow. When I was a kid, 8 was pretty much the highest number that we usually get. And, Typhoon 8, is not really too bad. The only thing they worry about are like, pots and other things that fall off, of buildings. But it's not heavy enough to like, blow trees out of the ground and stuff like that. So, So number 8 is not bad at all when I was a kid, but now it's like what, 11, 10th. 10th would be something that we get like, wow. Okay. Well, there may not be any climate change, but typhoons are getting stronger. Yeah, it's just a different name for the same thing. Yep. So it's called a typhoon, hurricane, and there's one more name for the same kind of stuff. I cannot remember. I think the Australians have a different name for that. So it's just a regional name for, a system like that. All right, so let's see how we can deal with this one, okay? So as a recursive, it's not particularly useful, is it? And typhoon are basically, okay, back to this. X not greater, it returns. Okay, it does a return type is actually void. Um, so it doesn't do anything, but it illustrates the concept of recursion. And how do I pass a parameter minus, to invocation of the same routine? So it does illustrate those. Is that okay? All right. All right. So what are we going to do with this one? Well, it's up to you whether you want to use this approach or not. So because I have that feature, I have to use it. So so we have return address being 0 byte away from where the stack pointer is pointing to, and then we have our only parameter, which is x, that is 1 byte away from where the stack pointer is pointing to. So I'm just defining these labels so that I can use the symbolic name x to refer to the offset of parameter x from where the stack pointer is pointing to. You absolutely do not need to use this. Okay? If you do not feel not make use of. All right. So having these things defined, I need to access the value of x. For several things, we need to use it for comparison. We also need to use it in case we have a recursive call. So regardless, we need to get to parameter x. So the way to get to it, if you want a much more structured way than the usual things like, okay, let's increment, decrement, and stuff like that, the much more systematic way to do it is to load the symbolic name into a register. You can use register B or register C, or even register A in the middle of a subroutine. I usually just use C, and then you add register D to register C. So when this is all done, C is going to be the address of parameter x. But I do know that after the add instruction on line 5, register C contains the address of parameter x. Does that make sense to you? Is the parameter first, and then return address. What C is. This of the parameter. So if there are no questions about this step, then the next thing I want to do is I don't want to know the address of x. I want the value of x. So an LD instruction would do that. So now C is actually the value of x, where I can use for comparison, and then later on, I can pass it along to the next invocation. So at this point, I can implement line 3 of the C code, which is basically a comparison. I'm comparing it to 2. So I need to load 2 into another register. Register A is fine, okay? Load 2 into A. And then we have to do the compare. So when I perform the compare, I have to kind of think about which way do I want to subtract from C or C from A. That becomes the entire thing when it. So we have a JCI instruction or JCI instruction. Basically, it will jump if less sideway. So I want to utilize that instruction, and instead of having to jump around things, so I'm going to put that instruction here first, okay? And then we have end if as a label defined in the future. So now we go back here and go like, how do I arrange the what do you think? Yep, subtract A from C is the correct answer. Okay, because so in this way, when C is less than A, when C is end up skipping whatever, and it means we don't do a single thing. Is that okay? Right? So that means between the JCI instruction and end if is where we want to put the code for the then branch, which is invoking the subroutine again, but this time we'll have x minus 1 as our argument. Okay? So I know many people will be very tempted to do this. Let's just decrement C and then jump back to F. No, it doesn't work. Okay? Reasons. The agreement is the parameter is on the stack, not in a register. C has the value routine, which F is expecting it. So that's why it's not going to work. Okay? What we need to do is to do it the right way. Okay? So with decrement C, we still need to do that because we need that value to push it on the stack. So now we decrement D, and then we STDC, which basically is pushing x minus 1 on the stack. Is that okay? And then we're going to call the subroutine. Okay, once we have the parameter on the stack, then we'll call the subroutine, which starts with LDI A with the return address. So from here on, we can specify the return address as .6+ as long as we use exactly the same sequence of code after that. So decrement D, STD with register A, and then JMPI, guess what? To F, because we are calling F from here. This from outside the sub. Nope, it looks exactly the same. Nothing has changed. Okay. And the subroutine that the caller is responsible to push the argument. The argument is still on the stack. The argument was pushed stack. Return address was pushed by the routine deallocates only the return address, which means the argument is still on the stack time again. But it has no use anymore. The subroutine call is already done. So that means we have to deallocate the argument at this point. So this is for deallocating the x minus one that we push earlier, because it you what if I do not take x minus back on the stack, get return. That pointer is no longer return address. It is now pointing earlier or call. So it's not lazy or not, it is not. All right. And we got nothing to do after the subroutine call, so we're basically all done with the then branch at this point. So at the end of the conditional statement, now we can just do a regular usual return to the caller. So that's really just a LD. I can use A this time, okay, but I'll just be consistent and use D. So this is going to be the return address, increment D to deallocate it, and then JMPB to continue execution in the caller. So that cursive subroutine. But relates to your homework assignment. Yeah, I hope so. That's 19. Good so far? Go ahead. Six bytes ahead of. So if you look at the LDI opcode as offset 0, then offset 0, offset 1, offset 2, offset 3, offset 4, offset 5, offset 6. The just then pushed on the stack as the. So are we good so far? Okay. Do you think this program is going to do what it is supposed to do? Do you trust me? Very good. I want you to be a voter. You get all the advertisements. This is, if I don't have enough time to read all the information, the way I do it is I vote by a scale. Okay, so I collect all the pamphlets and whatnot of different issues and for different candidates, and then I put it on the scale. Whoever has the least weight wins. If I get a ton of material for a particular candidate, that's the first person I rule out. Because that person spent way too much money on campaigning and stuff like that. Uh-huh. It's supposed to be a colon. Thank you. Thank you. Very good. So there we go. So Control A, Control C. Oh wait, we cannot do that just yet because we have the setup to have it actually do some calls. So we'll do LDI D0, reset the stack pointer. It's really not needed because when I reset the processor, all registers are zeroed out anyway. But it's good to emphasize that we need the stack pointer to be 0 before starting up anything. And then we'll how many levels of recursion do you want to go through? 8. We'll set it up for 8. And in this case, if I wanted to do 8 invocations, including the first invocation, what should I pass as a value, as a parameter, as an argument? Because it will stop recursion at 1. So if you want to have 8 invocations, you need, I think 8 itself would do. Yeah, because it's 8, 7, 6, 5, 4, 3, 2, 1. So that would give you 8 invocations. So we'll put 8 into register A, decrement D, store onto the stack, register A. So that's really just pushing 8 on the stack. And then we will push the return address on the stack, LDIA again, dot 6 plus, decrement D, STDA, and then JMPI to the subroutine, which is F. When it's all done, I need to deallocate the parameter. So by incrementing D, I have deallocated the argument, and then the halt instruction at the very end of the test. One is really to test the subroutine itself. It is not a part of the subroutine. It's really just a test. See whether it works. How can it look like if I have those of input. Is that okay so far? All right. So let's go ahead and find out whether it works or not. So we'll go to the assembler, go to this source tab, paste, wait until it's all done. I think this is quite a bit faster than my other computer. Otherwise, I'm returning the computer. Okay. See, the other solution is to have the screen itself to have kind of like a lens system, so that the screen can detect where I am and then adjust the lens so that when I look at it, it will be kind of in focus. That seems actually possible. True, but then, if I want to look at something else, then I still have that problem, right? Yeah, I have tried that in my other classes. But without this, it's really hard because I cannot really see it in details. Download this. Yep.
Have you included some documentation anywhere with regards to the new operations that are possible?
Yes.
Yeah.
Yep.
Oh, it's okay.
Yep. All right, let's restart the emulator, or is it already? Nah, it's still here. Okay, there we go. As long as I don't do any logging, I think it's going to be okay. But if you do any type of logging, it's best to close the emulator and then restart it. This is recursion.csv. And Control K. It's all done. All right. So this time, how do I make sure the program is working correctly? Well, the first thing we want to check is the stack pointer, because I want to make sure that the stack is balanced, which means register D should be 0. That's good to know. The second thing I can do, but only in this particular situation, because we don't have interrupts, is we go to the RAM content, and then we go all the way to the end. Well, it's already here, all the way to the end. And then we see, try to figure out what is on the stack. Supposed to have 8 levels of invocation. How many bytes does it take up for each invocation? 1 byte for the argument, 1 byte for the return address. So it takes up 2 bytes per invocation. 8 invocations would have used 16 bytes. So, but now the question is, well, do they first or the higher byte of the two, the argument with 8, right? And then the subroutine is supposed to decrement it for each recursion. So it goes from 8 to 7, 6, 5, and okay, so heck, we can look at the stack after the entire thing. Well, going down seems to work. What about the other bytes? Oh, the 0C and the 20. Those are the return addresses. So we can, that is correct also. In other words, we can go back to the assembler and go to location 0C and also 20 and see whether those are the places where the subroutine is supposed to return to. So now we go back to the assembler, go to the assemble tab, and then we try to look up 0C as a location. This is the 0C as a location. That is the place where, so okay, what about location 20? Let's check that out too. So location 20 is down a little bit. Location 20 is right here, which corresponds to, oh wait, that's 14. Because they're all in hexadecimal, we have to use column W to look up these addresses. So this is location 20, and it's corresponding to the increment D instruction, which is also right after JMP instruction. Turn to register, particularly register off the stack, we supposed to. So even though I did of RAM, I can still did. Do we have any questions at this point about these two sample programs that I have gone through today? Each one contributes one particular thing to what you need to do, but you kind of have to kind of splice the techniques of the two and combine those into one particular program to make your program. Okay, you can do that. And how are we going to test it? The biggest question is how do you test your code, not so much how you're going to write it. The reason why I made that point is because if you write your entire code first and then you try to test it, it's going to be difficult to debug it. Lines of code without testing it working, it would be difficult to point out which line is causing that problem. So what I do is implement this return add. Okay, part is the recursive for the mechanism of calling with a parameter and returning a value. You can just so once you think you have the whole thing done, values are you going to use to test your Fibonacci sequence? 6 in the sequence? No, that would not be a good way to test it. You test it first. F of 0 is supposed to be 0. Make sure that works. F of 1 is supposed to be 1. Test it. Works for the two base cases. Try. You want to try 2 once you have tested. Try 1, it works okay. Try 2, it gets you into up to the stuff can go wrong with the recursive step that becomes infinite. In recursion, it ends. Go for any recursion. So an infinite recursion can be a bug leading you pass in RAM pattern as well. You will see two return address, two return address. That tells you that in a recursive call is incorrect. Fix where to look to your program is tracing your code is going to be very helpful because at least you know what addresses it has gone through. Even if a program is not working, how to approach this particular one. Get a step. So if you have the first part 0 and not used, right? Now, if the program is not working, it seems to stop. Everything is slowed up. Realizing what bytes are actually, overwriting the entire thing, you can tell what the parameter is, and you can also tell what the return address is. So that way you can tell, okay, am I passing 2 every single time because I forgot to subtract 1 first before I pass it? So that's how you can test your code or look at the trace or what is left behind and try to figure out what went wrong with your program. Okay, so I would definitely at least take a look at the RAM content when your program, gets in, it's not coming back or doesn't seem to be working. Okay, slow. The questions to the program. Does everybody see the connection between the sample programs that I talked about today and what you need to do? Let's go out and enjoy the storm, and then we'll start the lab. I'm going to stop the recorder first, and then we'll all head out to the lab.